The things that we saw in the video earlier, they're talking about these different uh, applications, how things are changing today. There are self-driving cars. The police may go on and use different kinds of strategies to solve crimes, including computational tools. Now, the tagline on the video is called Digital Age Skill for Everyone. Now, we would like to break it down a little bit, right? So one of the things that the digital age, I think that kind of is getting clear from the video itself, right? So they talk about there are these changes where data is coming online, becoming on stream, and everybody has mobile phones, and it changes the way that we do things. Now the second word there is a skill, right? Digital age skill for everyone. Now why is it called a skill? Well, what is going to be the difference between skill and anything else that you might learn in a class? So Perlin, what is a skill? Specific knowledge. So it's something that you know. Is that right? Okay. Does anybody else has a different definition of a skill? Cheryl? What's a skill?
Something that you know how to do.
Something that you know how to do.
Yeah, like how to do instead of like just knowing it, but you know how to do.
Give me an example of one.
Coding.
Coding. Okay. Less nerdy one.
Like playing the piano.
Playing the piano. Okay. All right. Okay. Do you play the piano?
Yeah.
Okay.
I teach the piano. I teach.
You teach piano too. All right. Okay. Okay. Now, when you teach piano, what do? Do you give someone a book to read?
No.
No?
Like you teach like practical skills, right?
So
And
practical
both
skills.
Practical and theory.
Okay. All right. So and when you teach piano, you demonstrate. Okay. And you demonstrate it once, and will the person learn it at once?
Depends. If it's like a kid, definitely not so fast, right? If it's like an adult, definitely super.
Okay. All right.
But it takes time.
Okay. But the student has to do it.
Yeah.
Okay.
In order to learn.
In order to learn. Now, so let's do something that is a bit more general. Let's say other than piano. Let's say cycling, right? Okay, who knows how to cycle? More of you, right? Right, so cycling, everybody knows how to cycle. And you probably remember how you learned it too, right? You learn cycling probably by getting on a bicycle, right? Instead of, your mother probably didn't take you to the library to borrow a book on cycling. She didn't do that, did she, right? So she probably just buys a bicycle for you, and then you get on it, and you try to ride a bicycle. Now, over time, you learn how to cycle, but along the way you're going to fall down. But one of the important things about skills is that you learn it, you pick it up, and in most cases, if you master the skill, you don't actually forget it. So I'm not sure how many of you are actually riding a bicycle on a day-to-day basis, but I think for any one of you, if I just present you with a bicycle, you can ride it right away. Even the last time you did it was a year ago, 2 years ago, and so on. So computational thinking is a lot like a skill. I mean, we're going to tell you certain concepts in class, but the concepts are easy to learn in the sense that, you can recognize it, you see it, and you kind of understand this is the kind of skills that you need to do. But in order to actually do it, it requires a lot of practices. So a big part of the class is not just going to be the lecture. A big part of the class is actually attempting the problems, what we call like tutorial problems, so that you get a sense of how to practice these skills yourself. Okay? Now, the last keyword I would like to talk a little bit about is the notion for everyone. Now, why do we call it for everyone? I mean, why is it not just for people who needs to know how to code? Now, some of you are coming from other schools and you do things like marketing analytics, tech for business. I think a lot of it is because there is now a realization that the kind of things that you do in the workplace today does make use of computers a lot. And it makes use of computers because the scale of things, the scale of problems that we need to deal with are getting larger and larger. I mean, in the past, maybe you work for a company, you do forecasting, and then you'll be analyzing the sales data on a month-to-month basis and how this is going to affect things and so on. But today, the kind of data that you might have to be analyzing even for forecasting purposes could involve a lot more transactions, a lot more online data, and things like that. You can't do them by hand anymore. You got to use computers. So the computers are there to leverage, to augment the kind of things that you can do. But in order to work with computers well, you will need to understand some of the concepts on terms of how they work and what is the best way to make them work for you. Now, even if we look at things like what involves computational. So this is, I went to the SMU library and I just typed the word computational on the library and just to see what kind of books will come out. And it turns out that the notion of computational touches on almost everything now. I mean, of course, we have the sciences, computational physics. So they might need to build some physics model using some simulations, or computational social sciences, right? So in a way, looking at the way that social scientists used to study things, maybe through interviews, through analysis, but now they may have to go through Twitter, to go a lot of social media, and that requires some computational skills. Computational psychiatry, computational design, computational economics, finance, even computational analysis of sound, scenes, and events. And I think they are not limited to just these domains. It has applications across many other domains as well. Now, the reason why we want to learn computational thinking is to be able to use some critical thinking skills to leverage on the power of computing. Now, in that sense, we would like to have a better understanding of what is it that computers can do well, and in what sense will they actually help us to do our job better. Now, what can humans do better than computers? And what can computers do better than humans? Okay, so let's see, right? Now, what can computers do better than humans? Anyone? Gladwin, you seem to know? Calculations. Okay. Glenn? Analyzing. So what do you mean by analyzing? Computers do better than humans.
Depends.
Okay. Sujan, what can computers do better than human? Data connection. Do you say that? Data connection. You mean? Use computers to connect data. Okay, all right. Okay, so the root word of computer is compute, right? So it does well at calculations. They generally don't get tired. So, I mean, they will run as long as you provide electricity. They don't get bored. They will do the same thing over and over and over again as long as you want to keep it running. They don't make careless mistakes because they are very precise in terms of the way they calculate things. So there are certain things that computers can do well that we would like to leverage on those powers. Now, but what can humans do better than computers then? Is there anything else that we still do better than computers? Making decisions. Okay, such as?
Such as making decisions.
On what? Like deciding? Uh-huh. So what is the last decision that you make?
What to eat.
What to eat? Okay, all right. So you wouldn't trust a computer to tell you what to eat?
I can try myself.
Okay. Okay, all right. What else? What other things can humans do better than computers? Yes?
I think humans are more creative.
Humans are more creative. Okay. Would you like to elaborate?
I think that computers are unable to think. You can tell them to do something, they can do it
Okay.
very precisely, very calculative, but you ask them, can you show me a picture of a bee or something? They need to go through a lot of complicated algorithms to get to the point, right? If you show them a picture of a bee, right?
Yeah.
The computer won't know what's a bee. They only know that this pixel is yellow, this pixel is yellow, this pixel is black, but they don't know what the shape it forms.
All right.
But from a human perspective, they can tell it's a bee.
Okay. But even humans need to learn that, right? Even humans need to learn what a bee is.
Yes, which
So if you give the computers a chance to learn what a bee is, would they know what a bee is?
they can.
They can. All right. So, okay, but you're saying that the humans are better at creativity,
Yeah.
okay, creating things, okay?
Yeah.
Yep. Yes, Chabun.
Empathy.
Say that again.
Empathy.
Empathy. So can you define empathy for us?
I also don't know how to define it.
So empathy is a certain ability to sense the emotions of others. So to be able to share the same feeling or to imagine what it feels to be in that position. That's true. Human has a lot of empathy. I think to a lot of extent because humans, we reflect in terms of what we ourselves would do in certain situations. We can imagine what it would feel like to be in a different situation. So empathy is really related to, a lot of it is basically based on emotions. Now, this is something that has been studied as an experiment in a research project. This is a research project that is conducted at MIT, and they are trying to get a sense of how well humans can detect emotions of others. So in this experiment, they have a number of subjects. This is one of the subjects. So they try to simulate two different emotions. One is delight, the other is frustration. And this is not just acting. It's not just like, okay, now show me delight, now show me frustration. Because in that case, then you need actors, right? These are regular people. Now, to simulate delight, what happens is that this person sits in front of a computer. And then they will show this person a video of a baby. And the baby is just gonna be laughing. And most people will find babies cute and funny, and then when they see the baby laughing, then they will break into a smile, they will show a delightful expression. Now in the other scenario, to simulate frustration, they show the same person an online form. And then they ask him to fill out the online form. So then he will fill out the online form and so on, right? Then he will click submit. And then when he clicks submit, the whole form is going to reset. And then he's going to have to do it all over again. Now after 3-4 times of doing this, most of us will get frustrated. And then they capture all these things in video, and they take snapshots of these facial expressions. They ask other humans then to look at these two pictures and to tell them apart. So what is delightful, what is frustration? Okay, now let's put you to the test, right? So how many of you think that A is delight? Okay, all right, so a lot of you do. Some of you still think that B is delightful. Now, the actual answer, yes, indeed, A is delight, and B is an expression showing frustration. But of course, they don't test people just on this a single pair of images. They test them on different pairs of images, different subjects, and so on. And they look at the comparison in terms of how well human is doing and how well computers are doing. So now in terms of frustration, right, humans are operating at around 50%. Actually lower than random. So whereas computers that are specifically trained for this one task can perform at close to 100%. Now of course, this on the one hand, we think this is a very human task, detecting the emotions of others. But on the other hand, you can actually train a computer to do it if you give it enough information, enough data, enough opportunity to learn these things. Now, of course, this is still very much a very specific task. So they don't do this well for everything, and they have to be trained specifically only to do this. And the same algorithm probably doesn't do anything else well other than just telling these two emotions apart. But that gives us some sense of if you can isolate a task into something that computers can compute, chances are today there are going to be some algorithm somewhere that would allow us to translate this into a computer algorithm. And that allows us to do things in a more accurate way, in a more precise way, in a more correct way. Now, this doesn't necessarily replace the task of humans because there are still a lot of other things that we can do. And that allows us, think of it like a calculator, right? Instead of you having to tell the emotions of others, being trained yourself to do it, right? because in order to tell others, that means you still need to have some sense of the emotional range yourself. Now think of it as like a calculator is a way for you just to process pictures, process data, and then you get some kind of a probabilities of certain things happening or certain outcomes are being expected. And that is something that we can get help from the computers. Now, the kind of complexity of the tasks that computers can do are getting larger. And we can give a lot of illustration in terms of the different things that they can do. But one of these indications is based on the kind of games that they can play. So in the past, let's say 20 years ago, they beat us at chess. Now, but at that point of time, beating humans at chess just relies mostly in terms of the ability of the computers to do a lot of calculations. So they can do look ahead, several steps ahead, based on the current board positions, and they can compute what are the possibilities, and just based on that computability, they can beat human. That was then the era of this so-called supercomputers. Like they try to build as good supercomputer as possible. But over time, then they get to beat us at poker. Now, poker itself is really not simple, right? There is also a lot of variability, and there is bluffing involved, right? So it's not just like chess, like everything is probably a bit more precise. They can then beat us in Jeopardy. Jeopardy is a quiz show in the US where you need to analyze some text, and then you have got to arrive at the answer to a question or the question to an answer. And that means now to be able to sense Jeopardy. Now it's not, Jeopardy involves some kind of information, some kind of knowledge. Because for chess and poker, most of the information are in the game itself. So for chess, you know all the possible board positions, and you don't need to make use of any information outside. Now in the case of Jeopardy, there is a lot of historical facts that are being tested, or even some things about science, some things about history, which means that now the computers need to have the ability to remember, to recall, to parse natural text, and to be able to answer accurately. So this gives rise to a certain level of complexity. Now, one of the most recent ones is they beat us at the Go, right? So Google has a new algorithm called AlphaGo. Now here, of course, Go itself is a complex game, but one of the interesting parts about this latest development is that it's not just doing computing, it's the fact that this computer program is actually learning. So it means that as it plays games, it gets better at it. And that gives us a new range of algorithms that is not just being coded once and done, but actually learns over time. And that also allows us to get computers to do ever increasingly complex tasks. So what we want to do is that we want to learn to work with them. We want to put their strengths and advantages to our use. And one of the basic fundamentals to doing that is to understand the nature of computations and how we can shape the computation in such a way that we can to solve our problems. So we will try to do that in computational thinking, but it's really just the first step. We're going to talk about certain concepts that computational, what it means to formulate a problem in terms of something that can be computed, and how is it that we can design a solution that can be computed as fast as possible. Now, these are certain principles or elements of computational thinking. I think we call it computational thinking. It really doesn't mean to think like computers. It really means to think in terms of computation. Because once we can transform a problem in terms of something that can be computed, then we can actually run certain algorithms or design them. It's called conceptualizing, not programming. We are going to rely on programming to translate the thinking concepts into a piece of code. The emphasis is on the programming itself. If you don't know programming at all, you probably have to pick it up, and we're going to use Python in the class. But really, the kind of codes they're going to write in class are not going to be like thousands of lines. Most of the time it's going to be 10 lines, maybe 20 lines. They are not big codes, but they are certain kind of codes that try to explain a simple idea and in a way that is as the least complex possible. So in a way, what we emphasize is on the concepts. But there's going to be some programming element because we want you to be able to translate the concepts into some concrete thing. It's a fundamental, not rote skill. What we actually mean here is that it's a kind of skill they're going to learn, but it's a fundamental skill in the sense that we expect you to apply it to many different situations. So we will come up with some concepts, we will give you some problem to solve, and over time, the problem that you're going to see in the exam are not going to be exactly the same. Because then you need to be able to generalize from what you learn in class to new situations, and this is what we mean by fundamental, not rote skill. You cannot just remember it, because that will not be enough, because in reality, a lot of things that we see in the life is not, are not new things, because if it has been something that's been solved before, you can probably just use a previous solution to do the same. Okay, complements and combines mathematical and engineering thinking. Okay, so there's going to be some math involved. Just later today, we're going to be doing something called counting, right? It deals with ideas, not artifacts. It simply means that the important thing is the concept behind it. Let's say, for example, not just producing the code, but let's say how you actually produce those codes. Those are important for everyone, for everywhere. All right? Now, what we're going to do is that I'm going to show you a case study. And what I hope is that through looking at the case study, we are going to have some appreciation of what are the kinds of problem-solving skills we're going to learn in class over the whole term. Before we do that, I will show you this video on Google's computational thinking video, just a 3-minute video, and then we'll go into that case study. Now, the next part of it, I would like to talk a little bit about a case study, and we call it based on the kidney matching. So what we could do here is that, so all the content that we're going to use in class are going to base on e-learn, and we're going to use the combined section. So that's like G1 to 6. So under content, in week 1, there are a couple of files here. So there is a news article here, Channel News Asia, and there is a document that is called Kidney Exchange. So if you were to open those documents, right, so the news article is just a page long, and the other one is this notion of a kidney exchange, which is more like a worksheet. Now, we will take about 10-15 minutes just to look through these two documents, the news articles, as well as the worksheet on the kidney exchange problem, so for you to get a sense of what we are trying to do here in terms of the kidney exchange, and then we're going to discuss together as a class how do we actually go around about solving these kind of problems and what is important. Okay, let's take the next 10-15 minutes to do this, and if you want to, you can discuss with some of the people around you. Okay, so can I have someone tell us what the article is all about? Anyone? So, Royston, did you read the article? Can you tell us what is it all about? Donating kidney. Okay, all right. It's about donating kidney. But why does that make news? I mean, donating kidney has been around for a long, long time, right? Finding a compatible kidney for each recipient. Okay, all right. Now, does anybody else has any different opinion in terms of what makes news here? What is newsworthy here? Yes.
First pet kidney exchange in Singapore.
So is it the first kidney donation?
No, it's the first pet one. So the mother donates to someone else, then the daughter receives the kidney from another person.
Okay, so there is a barter trade here.
Yes.
Okay, so in this case there is an exchange. Now, okay, so why is it such a big deal? Why can't we just buy one? So they have a pair, right? So A can sell it, B can buy it, right? So what is the problem? Yes? Ethical reasons, okay. Yes, but more like legal reasons, right? I mean, we may be willing to, whether it's ethical or unethical, but in the case of Singapore, as it is in many other countries as well, organ transactions are illegal. So you cannot buy one. So because you cannot buy one, then you can donate one. Or you can get a donation from one. Now, most of the time, right, kidney actually supposedly is a slightly simple problem because everybody has 2 kidneys. And you only really need one. So what it really means is that many times people can actually find a willing donor. So everybody has a loved one, a father, a mother, a sister, a brother, a husband, a wife, a child, and so on. So most of the time, people can find a willing donor because a donor can still live with 1 kidney. But the problem is that just because a donor is willing doesn't mean that that is advisable to do so because they may or may not be compatible. Which is where this whole point about having an exchange then makes sense. Now, so we are going to discuss this problem a little bit just as an example of the kind of problems that might come, you might come across, and you could actually apply things that you learn in computational thinking to this kind of problems. Now, this is kidney donation, and as we said earlier, so we would like to facilitate an exchange between 2 couples. Now, we say couples, right? But it could really be a couple of anything. It can be a grandparent and a grandchild, it can be a husband or wife, and so on. But in this particular case, there are 2 pairs, Annie and Adrian. One of them needs a kidney, one of them is willing to give one. And then Brittany and Brian, one of them is willing to give a kidney to the other one who needs one. But the problem that we are facing is that Adrian cannot give to Annie, and Brittany cannot give to Brian. So which means in this case, direct donation cannot take place, then they have to find someone else to exchange. So, but in this case, right, how do they find one to exchange? So can do they just advertise in the newspaper? Is it, you cannot incentivize it, you cannot go into transaction. So most of the time the way that they get an exchange is that they have to register themselves to some kind of registry. And these registries are usually run by countries, like for example Singapore may run one, and they'll have a list of people who is willing to exchange kidneys. Now in that case, then the job of the registry is to facilitate these exchanges by finding which pairs should be exchanging with one another. So then we can formulate that as a computational problem. Because you can say, all right, so because I have so many possible pairs, I can investigate which pairs are going to be good, right? So then the notion of good itself is something that can be quantified. Now, one example of doing that, let's say, we can ask all of them to submit their medical data so that we can assess their suitability to exchange the kidneys. And let's say, for simplicity here, we give an example of 4 pairs, right? So A, B, C, D. Now, every pair, right, has 2 people. One is a donor, one is a recipient. So the A donor and the recipient and so on, right? Now, the recipient cannot receive donation directly from its own donor because they are not medically compatible. So in that case, that's why the diagonal is an A, right? Not applicable. Now, in any other cells of the matrix, you see some percentage value in terms of how compatible they are. Now, likely you want something that is compatible. The higher the compatibility, the more preferable it is, right? So we would like to minimize complications. We want to maximize that indeed it is a good match. So then we can form a problem whereby we're going to ask these 4 people to divide into 2 groups of 2s, right? If I can group A and B together, then A and B can go on one operation, and I can group C and D together, C and D are going to go on a different operations. Now, but if I just want to divide 4 of these pairs into 2 groups, right? How many possibilities are there? How many possibilities are there? 12? So how do you get 12? So we have 4 of them, A, B, C, and D. And we want to split them into groups of 2s, right? So one possibility is that you're going to say A can go with B, right? So if A goes with B, who does C go with? C will go with D. And we can call that one possible solution. Now, but does A have to go to B with B? A could also possibly go with C. In that case, then B has to go with D. And yet there is yet another possibility where A goes with D and B has to go with C. Now, any other possibilities other than these 3? Now, in this particular example, there are only these 3 possibilities, right? So now, even enumerating these possibilities is part of the computational aspect of the problem, because then we need to know what are the range of solutions that we can deal with. And this is some of the things that we're going to do later when we talk about the counting concepts. Okay? Now, of course, if it is just 4 groups, you can divide this into 3. But if it is 6, then it becomes a little bit harder. If it is 8, if it is 10, and so on, right? Then the number of possibilities are going to grow, and they're probably going to grow quite fast. Now, let's say for this example, we are given 3 possible options. So we can call it option 1, option 2, option 3. Now, which of these options are the best? So 1, 2, 3. So which one is the best? So Grace, what do you think? Depends on the compatibility score. Okay, can you do you work out some solutions?
Yeah, initially I did it just not this group, but just in
Just 2 of them.
yeah.
Okay.
So I would first rank the compatibility scores from highest to lowest.
All right. So you're gonna take all these pairs and then we're going to rank them, right?
Yeah.
Okay.
Then starting from the first one,
Yep.
the highest one, if it belongs to donor A.
Yep.
So then I would cancel off A because A would already be going to someone else.
Okay.
Then I would go down the list to eventually match the highest compatibilities.
Okay. So in this particular case, the highest one is 95. So then you will say that A must give to D. Okay. But you remember that D should also give to A. Right?
I didn't think about it.
Okay. So now, but you are describing an algorithm. That means you're already describing a series of steps that you're going to do to arrive at the solution. So I'm gonna sort all of them. I'm gonna rank them. I'm gonna pick the first one. I'm gonna remove the duplicates. I'm going to now all these are different steps that you need to take to arrive at the solution. Yeah. Now, if let's say you follow that, right, there is a way to actually solve the problem where you can go where A gives to D, but D doesn't have to give to A, right? D can give to B, B can give to C, C can give to A, right? Now, what's wrong with that problem? What's wrong with that solution? Is there anything wrong? So why do we do it in such a way that if A gives to B, or A gives to D, then D must give to A, and B gives to C, then C must give to B? So Luis, what do you think?
Logically doesn't make sense because like,
Logically, it doesn't make sense.
because I give you my kidney, then you give my kidney to someone else.
So it should be an exchange, huh?
Yeah.
Okay. All right. Okay. So it's like giving a present, huh? Then the present should not be given to someone else. Okay, but that's not what it actually means. It means that, A donor can give to B recipient, but the B donor can give to the C recipient, and the C donor can give to the D recipient, and so on. So that means they are passing the kidney to the other ones, right? There is a problem with that, and the problem is not computational. The problem with that is actually logistical. It's logistical because in order to do kidney exchange, right, you need to do surgeries. And you have to do, in every exchange, right, you need to do 4 surgeries. Well, you need to go to the donor, you need to take out the kidney, and in the next operating room, you have another set of surgeons who are going to put the kidney in. Now, that means that you need as many surgeon teams and as many operating rooms to do all these things simultaneously. Now, if A gives to B, B gives to C, C gives to D, D gives to A, effectively you need 8 surgeon teams, all operating at the same time. Now, why do they have to operate at the same time? Why don't A give to B today, B give to C tomorrow, and C gives to D on the next day?
Ethical issues.
Ethical issues. So what is the issue here?
That if, say, you have 2 operations first,
Yeah.
and suddenly, oh, I'm sorry, I don't want to do it anymore, something like that.
Okay, yeah, so you back out.
Yeah.
So if in the chain of this thing, somebody somewhere backs out, there is no way to compel the person to go through with it, because you're not supposed to go into any contract. So because there is no transaction. So it has to be done simultaneously. And because it's done simultaneously, most of the time for logistical reasons, we're gonna do paired exchange. A to B, B gives to A. 4 people goes into the operating rooms at the same time. Okay? Now, but that still remains that there are still different ways to score the solutions, right? Because then you have these 3 possible solutions. How do you tell which one is the best? Now, that comes down to what is the definition of being the best. Does anybody have a solution? What does it mean for a paired exchange to be good? Equal chance of survival. Okay, so how do you do this? Huh?
All being high.
All being high.
Yeah, but like BC and AD is like 3, 4, 5, like that.
Okay.
But then AB and CD is 3 lower, 3% lower, but their odds are even compared to the other ones.
So you're saying that you want it to be, it's like okay, it's like you're thinking of it like a price, right? So if I give you something that costs 80, you should give me something that is as close as possible to what I'm giving you. So that means here you'll be taking the differences and trying to minimize the differences. Okay.
The highest lah.
All right. Okay. Yeah. So that's one way, because then you have a certain way of thinking about the problem, when thinking that if I'm going to give you something, you should give me something of more or less equal value. Okay. So that's one algorithm, right? That's one way to quantify how good a solution is. Now, anybody else has a different one? Yes, Kidman.
I think I will go with, let's say if we pair, in the scenario 1, we pair A with B.
Yep.
And C and D, right?
Yeah.
We will get the highest average among all 4 percentages.
Okay.
Compare across all 12 options.
All right. So then you're going to sum up all the values for the 4, right? So A to B, some percentage, B to A, some percentage, C to D, D to C, and then you're going to sum them up and so on. Yes, that's a different solution. In this case, you have 2 different objectives. But in both cases, what you might want to do is to look at all these possible solutions, right? Now, you're getting a sense now of a certain points of things where, for the same problem, you can actually arrive at different objectives in terms of what it means to solve the problem well. Now, on the other hand, right, then we also want to think about, given that you fix your objective, how do you compute the best solution to fulfill that objective? So Kidman may say, okay, I'm going to sum everything up, average out. I still need to compute it for 1, I need to compute it for 2, I need to compute it for 3, right? And there are going to be a certain number of steps involved, because you need to do the sum, you need to do the averaging, you need to do the comparisons. Now, this sort of problems, right, it usually comes under the abstraction of what we call maximum weight matching. So it means that given some graph, right, we're going to talk about graph sometime in week 9. Given a graph, we are finding the edges that are going to be maximizing some value. And there is some algorithm to solve that problem. Now, let's assume that that is indeed the problem that we want to solve, which is to take the sum. So if we want to take the sum, then we are going to come up to a situation where just now among the 3 options, the option 2 is the best. So we're going to get to a situation where option 2 is going to be the best because it's going to maximize the total weight, which is the sum of the 4 numbers. So then we will conclude, let's go with option 2. which is a valid choice. Now, it turns out that supposing that you do go with this algorithm, there is another problem. Now, we can understand this point, right, from the notion of preference ranking. Now, of course, you know, when the doctor tells you, oh, the compatibility is 85%, to you it's just a number. It doesn't mean much of anything. To you, what is the most important thing is that you get the one with the highest. So even if you have 85, the other guy has 86, you want 86. The other guy says 86.5, you want 86.5, right? So in that case, you can think of this as every recipient has a preference over who they get the kidney from. Maybe one kidney is better than another kidney. So if that is the case, then we can analyze the following situation where your algorithm comes up with solution A gives to D, D gives to A, B gives to C, C gives to B. But if we look at this closely, we see that for A and B, it turns out that A has a preference for B rather than the one that you assign to it. So in this case, A prefers B to D because B has a higher percentage than D. And B itself also does the same. B prefers A to C. So B prefers A to C because B to A is 85, to C is 75. So A and B, they prefer one another to the ones that you're telling them. And because all these things are voluntary, there is no incentive for them to stay in the same arrangement that you have given them. Then they can then go off and break and go on to their own exchanges. Now, which means that you have solved a problem using an algorithm, but the people don't follow your algorithm. They don't follow the solution. So which means that at the end of the day, the job at the registry then will essentially come to nothing because then they realize a lot of people are not following through the recommendations. So now, when people analyze the situation, they understand that this is because of the concept of stability, and they realize that, oh, this notion of stability is important. It's important because you want to come up to a solution, you want the solution to be stable. The people are not just going to break off and do their own thing. Now, what is the notion of stability? The notion of stability is that you should not have this kind of solution where after the whole matching is done, there are still people who prefer one another to the ones that have been matched to. And this sort of problem is called stable matching. And it turns out that among the three options that we were looking at earlier, right, the solution A, B, C, D is the only one that is stable. Now, it may not maximize the sum, but each individual within the match cannot find a better match than the one that you give them. They may prefer someone else, but there will not be the case where that someone else also prefers them to whoever they are being matched to. Now, that is the concept of stability. Now, and let's suppose that you say, okay, let's figure out, I want stability in my solution. Because it turns out that this is going to require a lot of exchanges, and kidney is a life-changing thing, I want this to be stable. Then you still have to find a solution, right? And there are many algorithms to do that. Even for a given objective of stability, there are still many ways to do it. Now, you can do something that we call a brute force solution, which is to check every possible answer for stability. Now, if you do that, then the number of configurations that you will need to look at is going to be huge. So even for small number of pairs, let's say n equals to 22 pairs, you already have to look at 13.7 billion configurations. One by one, you got to count and you got to check, is it stable or not, is it stable or not, and so on. Okay? And these are concepts that we're going to be covering in later today in terms of how many that we're going to count, as well as in terms of complexity that we're going to do in week 3. Now, but it turns out that there is a solution to this algorithm. And this algorithm is called the stable marriage problem. And this was invented in 1962, which is called deferred choice algorithm. Now, this notion of marriages between men and women, they are only an abstraction. An abstraction meaning that they are describing a certain idea that are applicable across many different applications. So we talk about men and women in marriages, And the real concept there is that there are two different roles, being a man, being a woman, and there is a one-to-one match. So one man to one woman. Now in the same thing, right, in the kidney exchange problem, you have the same situation. There is a donor, there is a recipient. So there is a role there, and it's a one-to-one, because one person cannot give two kidneys, then he himself will not be alive, right? So in that case, then you can reduce them to the same kind of abstraction. And it applies in many, many situations. And in that case, then we just think of this as a way to simplify the problem. Now in this problem of kidney matching, as it is in a stable marriage, is to think of there are a number of men, a number of women, and we want to match them. Think of it as a global arranged marriage kind of a situation. You can choose who goes with whom, right? Now, one of the criteria that you may want to achieve is the stability. Stability in the sense that after I match everybody up, I don't want anybody to cheat. Now, the only way they can cheat is that if they can find someone else in a different kind of marriage, in a different marriage, they would also go prefer them to whoever their spouses are, right? So the same concept of stability is also there. And this can be solved using an algorithm that is going to go fast. And the algorithm essentially is matching men and women through a series of proposals. It's very intuitive. So you have a man, you ask the man to make a proposal to his most preferred woman. So the man is going to go up to the woman and ask, would you marry me? Then the woman would see. The woman is single, then the woman would say, all right, let's agree that we're going to go into an engagement, but let's not just get married yet. So then they'll be engaged, right? Now then the next man is going to go propose to his most preferred woman, and then we're going to go this in series. Now at some point in time, a woman may receive a proposal, a second proposal, when she's already engaged to another person. At that point of time, she will compare. Who among the two do I really prefer? So then she will then be engaged to whoever her most preferred one is. Then the guy is single again. Then the guy will just go on and propose to the next woman in his list. And all these things are going to go on until the end, everybody will have a fiancé, right? And if everybody has a fiancé, then they'll all get married together. Now, in this case, this particular algorithm is going to involve, in the worst case, every man proposing to every woman. But you are always guaranteed that you will find a solution that is stable by the end of the algorithm. It's guaranteed. There will be a stable solution. Now, what is the quality of this stable solution? Now, that depends on who is doing the proposal. Now, who do you think? Who do you think has the better deal here? The guys or the girls? The ones who are doing the proposing or the ones that are being proposed? Who has a better deal? What do you think? So, Shaflin, what do you think? Would you rather be doing proposing or would you rather being proposed to? So when you apply this kind of algorithm, right, you will get a stable solution. But a stable solution may be different depending on who is proposing to whom. If a guy proposes to a girl, you get a stable solution. If a girl proposes to a guy, you get a stable solution that may be different. And in general, if you look at the quality of the choices that they get, the ones doing the proposing gets better deal. Because simply, right, the ones doing the proposing, when they choose to propose, they look at their global preference list, they go to the very top, and they're going to try their best, the most preferred one first. The ones that are being proposed to are only choosing among the ones that come to them. They may like someone else, but the person never comes. So then in that case, then on averages, yeah. Now, why is it important? Now, we are not here talking about the quality of the marriages and so on. We are talking about the quality of the solutions, because it means that when you do have a situation where there are two different roles, the way that you process the algorithm is going to arrive at a different outcome. Suppose that you want to use an algorithm like this to process school applications. So students apply to schools. And the schools have preferences over the students. They all want the better students, or they want students of a certain kind, they know how to do certain kind of sports. The students would like to go with a certain kind of academic environment and so on. Students have preferences, schools have preferences. Whose preferences do you honor more? And that is going to arrive at a different outcome. And then, in that sense, even when you're trying to solve computational problems, the way you choose your objective matters, the way that you process the algorithm in terms of your abstraction, what kind of parties play what kind of roles are going to arrive at a different solution. Now, then you need to take into account all these considerations. Now, to the extent that computational thinking is doing all these things, we are going to be objective. There is no morality in the computations things. I think here we are going to go to the point where let's first agree on what is the problem formulation. Now, let's agree on the objective. Now, given that objective, how do you arrive at an algorithm? How do you arrive at a solution that is going to get you that objective as fast as possible? That is what we are going to do within the course. Now, beyond the course, when you try to choose which algorithm to use and so on, then you will come across all these domain-specific scenarios where you have to take into account, hey, my algorithm has certain kind of properties. When I apply it to this scenario, what is the best way to apply it? Because there are different consequences to the different choices in terms of what we are trying to do. All right? Now, the kind of problems that we are describing here is something that we hope you'll be able to go through the whole thinking process by the time it comes to the end of the course. All right? So in some sense, it does have elements of different concepts, counting, complexity, algorithms, and so on. Now, just to tell you one more interesting thing, right? This particular algorithm actually is awarded the Nobel Prize in economics. So it's given to two people. Shapley is the person who has designed the algorithm. There were actually two people. The other people is called Gale Shapley, so Gale and Shapley, but only Shapley is still alive. So he designed the algorithm, and Alvin Roth is an economist who applied this algorithm onto different kinds of economic markets where you cannot apply prices. So this includes matching doctors to hospitals, students in public schools, as well as the kidney exchanges. Now we talk about A, B, C, D forming two pairs, but actually the longest chain they have ever created is 6. So 12 parties, 6 donors, 6 recipients, kidney exchange in the US. They can't even do this in the same city. They have to do this across multiple cities. There are helicopters waiting in the hospital. They take one kidney, go away to some other places. So basically it's a chain. A gives to B, B gives to C, C gives to D, D gives to E, and so on. 6 pairs of 12 party was done at the same time. Okay? Now, any questions so far?